Shall we start or we wait? Okay, let's start. Okay, so welcome to the today's last session, which is about power systems. Sorry. Welcome to the last session, today's last session about power systems. So we've got a very interesting session with 5 papers, 3 of them about protection systems, 1 real-time simulation, and 1 impedance measurement. So we start with first speaker. The paper title of paper is ATP models differentiator smoother filter model validated using actual time domain relay, presented by Mr. Eduardo Passos. Yes, so sorry for the pronunciation. So you've got 10 minutes. Please keep the time, and we will have some time for the question and answer.
Good afternoon, everyone. Good afternoon, everyone. I'd like to thank your presence here today, and I'd like to thank you for watching us via YouTube. And also, I'd like to thank WCNPS for this great organization and for the opportunity. And my name is Eduardo Passos. I developed this paper with my professor advisor, Felipe Vigovino Lopes, and my teammates, João Paulo Ribeiro and Eduardo Leite Jr., which title is ATP Models Differentiator Smoother Filter Model Validated Using Actual Time Domain Relay. Well, it's known that traveling wave-based algorithms have gained notoriety among protection solutions for transmission lines. And as a result of that, fast and reliable techniques for detection of incident and reflected fault-induced wavefronts have been increasingly reported in the literature, where there are many filtering technologies used in TW-based applications, where the differentiator smoother filter, calling this paper as the S filter, is used in an actual time domain relay, the CL-T400L, where the DS filter original routines are embedded for protection and fault location solutions. And due to that, the DS filter has shown to be promising compared to another one. And the motivation of this paper is that the time domain relays are not readily available for many researchers, students, universities, and so on. And I mean to apply reliable DS filter in alternative transient program simulations for the study of TW-based applications. This paper's main goal is to emulate the TW detection method available in an actual time domain relay, the CL-T400L. And this paper demonstrates the DS filter implementation using ATP models language and how the DS filter was validated. This CL-T400L relay allows the usage of a playback feature used to realize the comparison between the models, the DS filter model output and the relay outputs. Well, as said, the DS filter is used in TW-based applications. So the understanding of TW phenomenon is necessary. And in this paper, figure 1 was used to present the period of fault circuit used to explain this phenomenon, where VF is the voltage step change generated in the fault inception time, RF is the fault resistance, ZS is the line surge impedance, and VTW and ITW are respectively the voltage and current TW launched on the transmission line in the fault inception time. And in this paper, figure 2 presents an equivalent circuit that can be taken into account to calculate the voltage and current TW at the fault inception time. And by 1 and 2, we can clearly see that the voltage TW amplitude can be calculated by the voltage divided between the fault resistance and the parallel of the line surge impedances. And the current TW amplitude can be calculated by applying the Ohm law between the voltage TW amplitude and the line surge impedance. Well, as soon as these TWs reach the monitored line terminals, step changes are verifying the current and voltage signals, and the DS filter uses these step changes to obtain the TW's amplitude. And a characteristic of the DS filter is that its outputs has a triangular waveform in response to input step changes. These characteristics allows an advantage of this DS filter. It outputs amplitude, is equal to the input step change amplitude, which means that the filter works with a unitary gain, facilitating the TW analysis of amplitude and polarities. Well, this advantage can be seen at figure 3b, and figure 3a shows a coefficient window of the DS filter, where in this paper, a window length of 20 microseconds was used, which means by 20 coefficients using a sample frequency of 1 megahertz. And the DS filter output is a result of an inner product between the input signal samples and the coefficient filter coefficients. And the unitary gain is only possible if the G gain of the coefficient window is properly adjusted. And to identify this G gain value, 3 stages are used in this paper to understand the output signal. Stage 1, while the coefficient window lies before the step change, presented by 4. Stage 2, if the coefficient window lies centered in the step change, presented by 5. Stage 3, while the coefficient window lies inside the step change, presented by 6. From 4 to 6, we can conclude that if the coefficient window does not identify the step change, the DS filter outputs will present a null value. And when the coefficient window lies centered in the fault inception time, it will present the maximum value equal to the input step change amplitude. And in this paper, the G gain value used to obtain a unitary gain was of 0.1. Well, figure 4 was used in this paper to show a simple DS filter algorithm that was used, which uses as input the 3-phase signals and as output the respective filtered signals. And in this algorithm is just needed to initialize the NDS coefficients and the coefficient window. And in the execution of the algorithm is needed to buffer the NDS samples of the input signal, compute the inner product between the NDS samples and the coefficient window of the DS filter, and store the results in an output signal. Well, the test point system used in this paper is presented by figure 5. The components parameters are present in the paper, and the 3 lines have 200 kilometers long each, and they are fully transposed. A solid phase A to ground fault at 70% of line to length was simulated in this paper with an incident angle of 90 degrees, and as a result, figure 6 presents a comparison between the cell T400L relay and the DS filter model. Phase A generated signals in the local terminal of the monitored line, and in the zoomed version, in the top part of the figure, we can clearly see the triangular waveform characteristic of the DS filter, and in the legend, we can see that the blue line presents the cell T400L relay output, and the dashed red line presents the DS filter output, and we can see that they match, that the DS filter works accurately compared to a real-world DS filter. And figure 7 was used in this paper to show a box plot of the absolute error calculated by 7 between the cell T400L relay and the DS filter model outputs in the first 60,000 samples from the fault inception time. And in the figure, we can clearly see that the major part of the errors are around 0.1 primary amperes. We can see that's not secondary amperes, it's primary amperes, which means that which means improve that the DS filter works accurately compared to the S filter in a real-world relay. Well, as conclusions, we have that the ATP model's DS filter works accurately compared to the cell T400L DS filter, and we have that the DS filter model is validated in this paper using actual time domain relay. And now a DS filter model is available for studies on TW-based applications, using 8P. Well, thank you.
Thank you, Eduardo. Questions from audience? No questions? So what is the advantage of using DS compared to wavelet transform? It looks simpler, but do you compromise some performance?
Well, we use the DS filter because this filtering technology is used in a real-world DS, in a real-world relay, the cell T400L. That's why we choose to use the DS filter. And the motivation of this paper is that time domain relays are not available for students in universities, as I said. And we want to turn this thing. We want to create our DS filter that can be used for researchers and for students.
Okay. Thank you. No other questions? Yes, please.
Congratulations, Eduardo, for an excellent presentation.
Thank you.
I would like to know what are the next steps of your research?
Well, me and Professor Felipe Vigovino Lopes, we want to emulate the functions of the cell T400L relay, like the TW87 function and TW2021, sorry. And that's it. That's our objective. Okay.
Okay. So please put your hand together again for Eduardo.
Thank you.
So we move to the second paper, two-terminal model traveling wave-based fault location method for HVDC systems, presented by Pedro Fernandez. Pedro was born in Brazil, 1994. He received his BSc in electrical engineering from UNB, Brazil. He is currently a master's student at the Department of Electrical Engineering, UNB University, and his research interests are focused on electromagnetic transients, HVDC systems, and fault location. So floor is yours.
Good afternoon. I'm Pedro, and I'll present to you the two-terminal model traveling wave-based fault location method for HVDC systems. Okay, HVDC systems have a lot of applications in power networks today. One of these applications that comes to attention is bulk power transmission, which uses very long transmission lines. So they are usually exposed to various environment conditions, thus they are more exposed to faults. In this manner, fast and accurate fault location is key to the process because it prevents damage to equipment, it quickens maintenance group actions, and as a consequence, it quickens electrical energy reestablishment to the consumer. But how can we achieve fast and accurate fault location in HVDC grids? One possible solution is by using traveling waves. Traveling waves in HVDC systems have the advantage of the line structure simplicity of the HVDC systems, and also to the fact that converter stations mainly reflect waves rather than transmit them. And there's a lot of traveling wave-based fault location methods, such as the conventional two-terminal method or one-terminal methods, but our work focus on a two-terminal model method based on aerial and ground modes. Okay, jumping now to the algorithm. The first step is to decouple the system by a model transformation. The HVDC system is analog to a two-phase AC system in the manner of decoupling. So if we apply 2x2, this is the Kahren-Bauer transformation matrix, we can decouple the bipole into aerial and ground mode voltages and currents. Once it did that, we need to filter the signal in order to detect the traveling waves. In this work, we use the differentiator smoother filter, which is simply a smoother block, which is just a low-pass filter in series with a differentiator block. And the work is just like Eduardo explained. You have a step input, and as an output, you have a well-defined triangular waveform, which will be your traveling wave. After you did that, you need to estimate the arrival time of the traveling waves on the monitoring terminals. And we achieved that by a simple direct comparison using a threshold. This threshold is based on comparing the amplitudes of the current signals of two consecutive peaks. Okay. Now that we have our traveling waves and the arrival times, we can talk about the fault distance estimation. Using this lattice diagram, one can compute this formulation by the first traveling waves of aerial and ground modes coming into the monitoring terminals. It's important to notice here that this formulation here does not depend on line parameters or data synchronization. And it is a PU measure. Keep in mind that we use the PU, the per unit system measure to locate our faults, but we also use the fact that we knew the line length by the simulation model to estimate in meters, just for convenience. Now, a brief description of the system we studied. This is a transcription from PSCAD to the ATP and ATP draw softwares of the Madeira River bipole. This is the first bipole. There are two bipoles, and they both operate at this specs right here. And this is the line length we used, 2,450 kilometers, which is a very extensive line. Okay, how we evaluated the performance of the two-terminal model fault location method. We studied pole-to-ground fault scenarios divided by 3 classes. Fault location variations from 1% to 99% of the line with 1% increments, and fixed fault resistance of 1 ohm. Line parameter inaccuracies, adding a plus 10% error on the aerial and ground line inductances. And the last scenario was the fault resistance variations from 0 to 1,000, which is a very, very high number. 1,000 ohms with 100 increments at fixed fault locations, which were 25%, 50%, and 75% of the line. For fault location variations, we use the cumulative frequency polygon technique. Here, to evaluate the best method, you need to look at the slope of the curve. The higher the slope, right here, the higher the number of cases with smaller errors associated with it. And for the two-terminal model method, which is the green one, almost 98% of cases have absolute errors that are close to 211 meters. We also use the box plot approach to understand the outliers of the method. And the two-terminal model method presents 3 outliers that are represented by the red crosses. But these outliers are still smaller than the upper limit from conventional two-terminal method, which implies that our measures are still good. Now coming to line parameter inaccuracies, I brought again the equation for the fault location estimation, just to show that, in fact, the performance is the same as from the fault location variations because the method does not depend on line parameters. Just to keep in mind that the two-terminal conventional mode depends both on the propagation velocity This velocity here is the aerial mode velocity, and also depends on the line length. Finally, for fault resistance variations, we plotted on this table the mean absolute error in percentage and also in meters. The results are very small, but there's another good performance showed here. The two-terminal modal method absolute error is roughly, it's a little more than 3 times smaller than the conventional approach. So jumping to the conclusions, the two-terminal modal fault location method indeed is effective for locating pole-to-ground faults, since for fault location variations, almost all the errors are smaller than a conventional tower span. The method is invariant to line parameter inaccuracies, and also it presents small errors facing fault resistance variations. Therefore, it proved to be an interesting alternative to locate faults in HVDC grids. Thank you.
Very interesting work. Any question from audience? Sure.
Okay, congratulations for the work.
Thank you.
And my question is not so technical, okay? I can see your approach is much better than the conventional one.
Okay.
In everything. How can you explain that in simple words for someone that doesn't understand the details of your work? Why your approach is so much better? What do you think is the difference?
Okay.
This is important when they are going to sell idea for other people. Okay, that's why I'm doing this kind of question.
Okay. Truth be told, the two-terminal conventional method can operate for pole-to-pole faults. This is just the pole-to-ground, so I may be questioned about it if it was a company. But I'll say that for pole-to-ground faults, it is very, very precise, much more precise. And for such long line lengths, such as the Madeira one or the Xingu Estreito, which is the other bipole here in Brazil, you can, how can I say that? You can use more precisely your time, because you will not need to look for the fault location in long tower spans. I present.
I was thinking more from theoretical side. Why is much better? I see it's much
Okay.
better, but what kind of information you have the other approach doesn't have?
Okay.
You don't need to know the answer, okay? But
Yeah.
this is the kind of depth is very important for students.
Okay.
I always say that for my students. In the end of a very complex work, you have to know how to explain that in very simple words. That's
Okay.
very good. Oh, this way to say.
I brought
Hey.
help.
May I help, Pedro? It's very simple. It not depends on time synchronization, and it not depends on line parameters. Just that.
Thank you, Professor Felipe.
Everybody knows you know that, okay?
Okay, yeah, okay, okay.
Okay, no other questions? Thanks again for
Okay,
the
thank
excellent
you.
work. So we move to the third paper, traveling wave-based differential protection applied to hybrid transmission line with multiple sections, presented by Caio Muller, if I pronounce it correctly. So Caio was born in Brazil, 1995. He received his bachelor degree in electrical engineering from UFG in 2016 and master degree from UMB in 2018. So floor is yours.
Thank you. Thanks, Professor. Good afternoon, everyone. Good afternoon, everyone. My name is Caio Miller, and I, together with my professor, Felipe Lopes, did this paper about the traveling wave-based differential protection applied to hybrid transmission lines with multiple sections. Well, Currently, time domain protection functions are those with the shortest operating time. Among these functions, those based on traveling waves, in which it stands out the traveling wave-based differential protection, TW87 function. Moreover, hybrid lines are becoming increasingly common. You can define hybrid lines as transmission lines with the different electrical parameters along the length. For example, TL's transmission lines with overhead and underground cable section. Well, with that said, the goal of this paper is evaluate the TW87 performance applied to hybrid lines with multiple sections. Well, the TW87 operating principle is presented on this picture. Well, basically, when occur an internal fault, traveling waves are launched from the above terminals. Due to polarities, the current transformers, for internal faults, current TWs at local and remote terminals have the same polarities. However, for an external fault, the opposite polarities. And for internal faults, P, the interval between the incident instants on the terminals, is shorter than the time TL transmission line propagation time. And external faults, P is about the same tau. Well, in this way, for an internal fault, two signals are created, operate and restraining signal. In such a way that for an internal fault, IOP, in operative signal, has high values, and IRT, low values. Thus, TW87 operate. However, for an external fault, IRT has high values, and IOP is about the same 0. Well, the numerical implementation. Firstly, the current TWs are extracted from the monitored signals by means of the differentiation smoother, DS filter. Thus, it's possible to calculate two amplitudes, TW87 variables. IOP is the operate signal amplitude, and IRT is a restrained signal amplitude. Based on these two amplitudes are created the tripling logic. If IOP is more than S multiply IRT, TW87 operate. Otherwise, if IOP is less S multiply IRT, TW87 restriction, whereas there is a restriction factor called here slope. To exemplify the problematics of the TW87 application on hybrid lines, we will use a 200 kV 60 Hz test system formed by unmonitored transmission lines, 200 kilometers long, and TLs adjacent on and adjacent to 100 kilometers long. In total, 408 short circuits were simulated using the alternative transient program. only external edge folds with inception angle equal 90 degrees at the middle of TLs adjacent on and adjacent to. Well, before we go to results, let us go to understand the possible problematics that can arise when applied the TW87 on hybrid lines. Due to difference between electrical parameters for each hybrid line sections, the amplitude of current TWs is modified when to pass at each junction point sections. As a consequence, the TW amplitude changes along the hybrid line. Being possible to estimate the TW87 values with reflection and transmission coefficients. It was not said that arise in minimum values the restriction factor slope. For example, two hybrid line with 2 and 3 sections is more than 0.3, 0.5, 0.3, 0.5, and 0.5 for external folds. Well, as we will see with the following results. Well, obtained analysis results. As only external folds are simulated in this paper, it is expected that if IOP is less slope multiplied IRT, the TW87 restrained correctly. But if IOP is more than slope multiplied IRT, TW87 operate incorrectly. In this paper, slope S equals 0.4, 0.5, 0.6, and 0.7. Well, let's go to results. In case on, when monitored TL is overhead transmission lines, for external folds on TL adjacent on and adjacent to, the TW87 did not operate for analyzed external folds correctly. But in case 2, monitored TL is a hybrid line with 2 sections. For a external fold and TL adjacent on, when length of underground cable section is more than 0.6 and 0.8 kilometers, the TW87 operate incorrectly. In case 2, for external folds in TL adjacent on and TL adjacent to, TW87 restrained correctly. In case 4 and case 5, in main case when length of underground cable section, the TW87 operate incorrectly. Well, in a global case evaluation, present here, case 1, case 2, case 4, and case 5, in hybrid line with 2, 3, 4, and 5 sections for external folds and operate incorrectly for this case. It's not said that when small slope as values are used, such as slope equals 0.4 and 0.5, more incorrect operate case occur. And the greater the number of hybrid line sections, the greater the TW amplitude variation. Consequently, more change of the TW87 to operate improperly. Finally, is conclusions. In this paper evaluated case in monitored TL is a overhead TL in hybrid line with 2, 3, and 4 in 5 sections. For cases on hybrid line, the length of the underground cable section was varied. The TW87 hybrid line required some restrictions in relation to length of the underground cable sections and number sections. Finally, minimal restriction factor S values should be used to guarantee the protection security. And that's it. Thank you. Thank you.
Thank you, Caio. Questions for Caio?
Thank you, Caio, for presentation. So I think it's a quite important type of study because this kind of the protection function has just released in the market. So it's a kind of some instruction for user in this kind of protection function. But in your opinion, so one can see from your results the protection function may fail, and it's not possible to guarantee the protection security for several cases. So in your opinion, even though you have did your master study using this function, for the sake of security, protection security, is it better to block this function or to set a high setup, pickup?
Thank you, Professor Kebler, for your question. I think that necessary use the high slope values for external faults. For external faults, the TWSF is not operate. But when use high slope values, the TWSF is lose sensibility for internal faults. I think that application TW application on hybrid lines, I think is blocked. Principally use multiple sections because TW change small change.
Okay. Have you already evaluated the other protection functions of the T100L relay using hybrid lines?
Sorry, I didn't
Have you
understand.
already evaluated the other protection functions
No,
available in the T100L relay? Okay.
not yet.
Okay. Thank you.
Me, not yet, and other student, yes. Professor Philip Lopes.
I have just a brief comment because before deciding for blocking the function, maybe we can analyze the cost benefit between the protection security and the cable line length. Maybe we can indicate that this kind of function is not suitable for lines with much cable. As you can see, if we use some slope values, if we have short cable lines, we can have proper operation for internal and external faults. That's why they put in the relay manual that they do not want much cable.
No other questions? Okay, thanks again. So the fourth paper is about real-time simulation, methodology to perform real-time simulation of power systems using an FPGA-based platform, presented by Marcos Sergio Leal. Marcos received his bachelor in 2017 from UFRN, and currently he's a master's student there. And his research interests are power system modeling, power system real-time simulation, power system protection, renewable energies, and signal processing. So, floor is yours.
Okay. The work is is going to be presented here is about a methodology to perform real-time simulation of power system using an FPGA-based platform. So the real-time simulation of power systems allows conducting studies in a perspective closer to reality. And one of the main reasons is due the possibility to perform a hardware-in-the-loop real-time simulation where we can have a control or protection scheme in a closed loop with a system being executed in real time. Also, you can have a commercial relay in a closed loop with a real-time simulator. Also, we can perform study over the power systems in real time, and we can validate and test our own models in real time. So if you take a look at the literature, we see the powerful ones, real-time simulators, like the RTDS and the Opal RT. They have a powerful computation, and you can model larger power systems using these real-time simulators. And you have a low-cost real-time simulator. If you don't need to model larger power systems, you can use a low-cost real-time simulator, or you can design your own real-time simulator. And you will have more flexibility to perform your simulation, like to choose your time step according to your application. So the motivation of this work is didactically highlight the many steps to perform real-time simulations of power system, and also implemented a relay and place this relay in a closed loop with a real-time simulation. The case study used, it was this system. This system was composed by a source, an RL branch, a resistant inductive branch that forms a Thevenin equivalent, and two transmission lines, but representing one transmission line, because with this we can vary the point of the fault. Fault circuit, and we have the relays. So the target device used was the single board RIO 9637, and the power system was modeled in the FPGA, and the relay was modeled in a real-time processor, but these two things are in the same board. But these two things is in a closed loop. The relay was the loop that handled the relay, operates at 1 microsecond, and the loop that runs the power system models runs at 20 microseconds, the time step. So here we have the AMTP models used to model the power system. The lumped element was modeled as can be viewed mathematically as a current source in parallel with equivalent resistance. The transmission line used in this work, implemented, was the Bergeron model. The sources, we use an actual signal source, but the reason is to have a signal and to use as an external thing into the simulation. And a piece of data processing to duplicate, to make a copy of the signal, a shifted copy. The switches model as a time-controlled switch. The representation is an ideal representation. There is resistance equal to 0 and equal to infinity, representing the closer and the open conditions. And a switch operation means a change in the topology of the power system. So you have different admittance matrix for each switch operation. The circuit break, the circuit breaker represent the switch represent the circuit breaker and the fault circuit. And the network solution, which is used for find the voltage at the nodes. Here is the computational model, the computational view. So we can see the system can be computed in parallel. The Bayesian model allows it. And here is the physical setup of our real-time simulator. We have the board, the signal generator, and a graphical user interface. And when you can set parameters like the power system parameters, the fault parameters like the distance, the resistance, the voltage at the fault point, we can choose also. The protection parameters, we model here a distance protection. So we can set up the protected zone, the nominal current, the overload factor. And we can see in using the indicators, the voltage and the current measurement, and the phasor estimation result, the execution time. So here is the architecture of the real-time simulator. So we have a real-time processor and an FPGA. In the real-time processor handles the graphical user interface. We have a step of pre-calculation to form all the possibilities of the admittance matrices. So this information are passed to the FPGA. Also, on the real-time processor, we have a producer loop. In this producer loop are implemented the relay. They receive the information of currents and voltages from the real-time simulator and send it back a signal. In the FPGA, we receive the parameters, and we have the AMTP loop. So we have a step of computing the current source, depending on historical currents, and also the voltage computation at the bars, and the updating of the current sources. So the FPGA, the time step chosen was 20 microseconds, and the execution time that the FPGA compute, the power system, was 6 microseconds. So we can reduce more the time step until a value closer to 6 microseconds. Or we can choose a time step greater and model more complex power systems. Here is a comparison between the real-time simulator, the MATLAB code, and the Simulink result. So we can see that all the waveforms are overlapped in the steady state and in the transient regime. It was a fault in 2 seconds, a fault distance 200 kilometers, and a fault angle of 60 degrees. Here is the same result, but for the voltages. And here is the impedance calculated by the relay. Here are the impedance trajectory. So in this work, was shown a methodology to perform real-time simulation. Also was shown an implementation of a relay placed in a closed loop with the power system. And this work is of greater importance because it will be of great importance for the development of protective relays, prototypes, for instance. And for future work, we will increase the complexity of the power system and carry out the studies applied to the traveling wave-based relays. Thank you very much for this presentation. This opportunity.
Thank you, Marcos. Questions for Marcos?
Congratulations for the work. I have 2 questions. One very stupid, and the other even more. Okay. How difficult is to build new models in this kind of FPGA? For example, if I decide to study some subsynchronous resonance in the wind power generator with GFIG, It's very hard to build these new models or not.
It's very
Hard, difficult. Okay?
no.
Just one more question. Where is barrier of hell?
Oh, okay.
If you don't know Portuguese, someone is from the barrier of hell. Where is that?
No,
Barreira do Inferno. Onde que fica isso, cara?
is based on Rio Grande do Norte.
Oh, okay. So the first question about how difficult it is to include new models, how difficult it is to have more generic simulators by using this kind of technology.
Oh, okay. Knowing the models, also the computational models, is difficult to implement it in hardware, but if you know the process, ended up to turn simple to model this stuff. But there is some issues on implementation. But if you know the modeling steps and the behavior of the systems, if you can analyze, and you can easily.
Maybe this kind of solution is more for specific studies than to build a more generic simulator.
No. It's
to
possible to yes.
Thank you for the very interesting presentation. Follow-up on stupid question, stupid questions.
Okay.
We know that RTDS and OpenRT are real-time simulators, and they are quite expensive. So you came up with a solution that seems to be much cheaper, and from your answer to the previous question, you can even model very complex power systems. So my question is, what are you losing, or are we just spending huge amounts of money to buy real-time simulators?
He wants to know why he has RTDS there.
Okay.
Yeah, exactly. Was I so stupid to buy an RTDS?
The platform, the target I'm using, the cost is about $400 for an instance.
Okay.
So using this hardware I'm talking about, there's limited resource, of course. But yes, you can increase the power system simulation with one technique. I will explain. You can, for instance, for transmission line, you have 15 transmission lines in your system. You can, if you have limited resource, you can share a unit of computation. If you have a target with high clock speed, do you understand? So you can increase, if you have some knowledge about how program the models, you can model bigger one, but here there's a limitation. Okay.
Okay. So basically, if I understood your answer, scaling it up.
Yes.
Is the problem. If you want to scale it up,
you need another hardware. You can have another hardware and increase your power system, the complexity of your power system. If you buy the hardware and use, for example, a clock and to synchronize this hardware, so it's a solution.
All right. Thank you.
I can add to your question. So. But the problem with the FPGA, of course, it's much cheaper, but the problem first is scalability, as you mentioned. So we cannot simulate large power networks like RTDS. So I'm not sure how many nodes you can fit, but maximum you can fit 5-10 transmission lines on the FPGA. Yes. The other problem is the fixed point calculation. So you cannot use double precision, and that limits the accuracy.
Yes.
He's so happy now.
Yes.
Okay.
Okay. Other questions? Sure. Flip.
My question is not related to the models you have implemented, but I would like to know only if some solution to avoid numerical oscillations in your system calculations, if some solution on that have been considered.
In the simulation I performed, I didn't have the numerical solution.
Oscillation.
Oscillation. I didn't have, but I already see this, and there is some ways to overcome this. In the MTP theory book, there are ways to overcome this. So.
But now you are not using this.
No, I'm not using.
Okay.
But
Okay, thanks again, Marcus.
no.
So the last paper and the last speaker, real-time impedance estimation in grid connected PV systems using the DFT, presented by Yuri Ribeiro Damasceno, if it's correct. So Yuri received his bachelor from UFRN and his master again there, yes. And now his research interests include renewable energy sources, DGs, microgrids, and smart grids. So floor is yours, Yuri. You have 10 minutes.
Good afternoon. My name is Yuri. I will present this paper. As you can see, I'm not an author of this paper, so they could not come. A lot of things happened. So I will present their paper, and I'll do my best because this is not my area of research. So I'll skip this. Basically, what is the motivation? The conventional power systems have changed by the addition of renewable energy resources in the distribution grid. And this happened because of environmental issues of the conventional generators, and also because there are advantages to install these in proximity to the local loads, and also it can increase the system reliability. But this new configuration implies changes in the monitoring, control, and protection systems. Therefore, it's necessary to investigate the system parameters under these changes, and a relevant parameter is the impedance. The knowledge of the network impedance can be used in control systems to improve the system response, and also in protection systems as an alternative to detect systems disturbances, such as islanding conditions and ground faults. Therefore, the correct impedance estimation is a useful tool for improving the performance of the system under this new configuration. In the literature, the impedance estimation can be classified as basically as two classes: the passive methods and the active methods. The passive methods, they work by collecting signals from the grid for a point of measurement, and they use these signals to calculate the impedance. They do not inject any signal in the system, so they don't affect much of the system, and they don't degrade the system's power quality. These methods, these passive methods, they have good performance when the system variations are affected the non-stationary signals significantly. But when these variations are not so big, they are small, they cannot detect the variation and they basically fail. So they have a big no detection zone because of this, and that is the main disadvantage of these methods. On the other hand, the active methods, they do inject a signal in the system, usually a high frequency signal, and they observe the system response, and they calculate the system impedance based on this response. Generally, they have a high signal-to-noise ratio, and because of this, they have a very small no detection zone. But one drawback of them is that they do degrade the system's power quality. As I said before, they collect the signals and they need to process them. And for both methods, it's necessary to use some signal processing technique and to estimate the impedance. In the literature, it is found a lot of techniques, and especially the recursive least squares, RLS, the discrete wavelet transform, DWT, and the discrete Fourier transform, DFT, and also Kalman filters, and others, but these are the more important ones. In this work, it was used the DFT because the simple implement, it has a good performance. It is easy to implement, and it has a low computational effort. And also an active method was used to estimate the system impedance in that current signal was inserted in the system, and in the current reference of the PV-based system, and the power quality, but the power quality impact will not be verified in this work. So the system is a microgrid, basically, with a PV generator, PV-based generator, rated at 8 kilowatts peak, connected to a point of common coupling. And the point of common coupling is connected to the main grid through a three-phase 15 kVA transformer. Between the PCC and the transformer, there is a additional impedance that is normally short-circuited, and this is used to emulate a change in the grid impedance. This microgrid has also loads, a linear load and also a non-linear load to emulate changes in load. Basically, the impedance estimation uses the DFT with this formulation, and the DFT coefficients are calculated by this first equation, where XH is the vector, the complex vector of the DFT coefficients, and H is the component that we are that we are trying to collect, and this big N is the sample window. That's the samples in the window, and K is the current sample. The real part is dependent on the cosine. The imaginary part is dependent on the sign. And using this formulation, the vector for the voltage is obtained, and also for the current. And they are, when the impedance is calculated by dividing the voltage by the current. This evaluates to the impedance at the frequency of the signal, injected high frequency signal. So it needs to be translated to the fundamental frequency. That's where we want to estimate the impedance. The resistance part does not vary with usually does not vary with the frequency, so we need to adjust just the reactance part. This is done by this last equation, in which we have the omega 1, that's the fundamental frequency, angular frequency, and omega f int, that is the frequency, angular frequency of the high frequency signal. The disturbance is not an integer multiple of the system fundamental, because sometimes the grid is disturbed with a lot of harmonic components. So it was selected the frequency selected was not harmonic of the fundamental, and the window size must be large enough to be able to extract the coefficients, and the injected signal is bigger than 10 times the fundamental frequency, and it's also not harmonic of the fundamental, and it was used as a 3 amp current to do this. And two scenarios basically were tested. One, a pure resistive component was added to the grid, and two, the complex impedance was added to the grid resistance. And this is the results obtained. On the left, the pure resistive case. On the right, the complex case. On the first, we have the impedance, the model of the impedance. The second is the resistance part, and the last one is the reactance. In the pure resistive case, we can see that the reactance does not vary, which is expected, and the resistance added was 0.5 ohms, and we can see that it represents it follows this addition. The estimation can follow estimates correctly. In the reactance case, we add a 0.5 ohm resistance in association with the 500 microhenry inductance, and it can be seen that the reactance also rises when we add this impedance, and it rises just the amount of the corresponding to the 500 microhenry reactance. There is a delay because we use a estimation process. And this delay is shown here. It's a zoom of this area. And it is 2 cycles because of the window chosen. And what's the use of this? There is, for example, a European standard that says that if an impedance change of 0.5 ohms occurs, we should isolate the supply, the system, within 5 seconds. So the future works, we use this impedance estimation to perform these decisions, especially for islanding situations. So, what's an active method was proposed in this work for estimating the impedance in a grid-connected PV based on the DFT. It had a good performance in an experimental platform in the presence of linear and nonlinear loads. And it's also able to correctly estimate the resistance and reactance components separately of the grid impedance. And as I said, in future studies, it will be used to detect island conditions, and also the impact on the power quality will be investigated. So thank you.
Question from audience? No questions? If not, I believe we can conclude the session. So thanks again for attending. Thanks again for all the presenters.
Thank you.
And see you tomorrow.